If you take a spring and push against it, you can compress it. And whilst it's compressing, you're actually applying the force over a distance. Since you're applying a force over a distance, you're doing work, and then once you've compressed that spring to the tightest point, to the point where you're not going to compress it anymore, and you hold it there, everything seems very still. You know, even though you've done work to the spring, the energy is not in the form of kinetic energy, as it would be if you just pushed a block along an ice rink. It's actually in the form of spring potential energy. So we use U to symbolize potential energy, Ug is gravitational potential energy, Us is spring potential energy. The formula which tells you how much spring potential energy is inside that spring, or how much work you've put into the spring, is Us is equal to 1/2 times K times X squared. K is Hooke's constant. If K is big, it means it's a stiff spring and there'll be a lot of energy in it. And that's true. If it's a very stiff spring and you compress it by a certain amount, you'll put more energy into it than if you were to compress a very loose spring. If you then relax that spring, so say this box has been compressed and that spring there is under strain. If you then let go, this spring will extend that way, like so. And the box will go shooting off like that, to the right. The kinetic energy of this box will be equal to the spring potential that was in the spring. That's the basis for the question we're going to do. So it starts off compressed, then it springs off. We've also got two different springs molded on the side here. Spring Z is stiffer than spring Y, because for every meter that we compress spring Z, it applies a stronger force here than spring Y. Now, setting up the question, let's make this block here mass 200 grams, or straight away I'll put that into kilograms, 0.2 kilograms. And part A, we'll say A, spring Z, compressed 10 centimeters, and the goal will be to find the velocity of the block, to find first of all the kinetic energy of the block, then the velocity. So spring Z, only look at the red line, ignore the yellow line for now. If we compress it 10 centimeters, this is 1 meter here, so 10 centimeters is over there. There are two ways to find the energy, spring potential energy in that spring. First of all, we should find the K value, the Hooke's constant, of that Z spring there. Since F is equal to Kx, and we can take this point here, 200 is F, and X equals, that shouldn't be 20, that should be 2. Then we can say that 200 is equal to K times 2, or the K for Z is equal to 100, dividing 200 by 2. The K value for Y is equal to 1/2 that, it's 50. Now the energy stored in Z is what we want, because the energy in Z, Us, is going to be equal to the kinetic energy of the block. The energy is actually equal to the area under that red line before the 10 centimeter mark, or the 0.1 meter mark. That area is given by 1/2 base times height. The base is given by x, and the height is given by kx. That's a bit tricky, but the height is given by the gradient times the run. But what we can do is just plug in this formula straight away. Ek is equal to what was in the spring potential energy, which is equal to a half k x squared, or a half times 200 times 0.1 squared, which comes to, that's 100 times 0.1 squared, and that is 1 joule, I think. Let's try that out. 0.5 times 200 times 0.1 squared. Yeah, 1 joule. So there was 1 joule of spring potential and energy in the spring, and therefore there will be 1 joule of kinetic energy in that moving box once it's launched off there. The velocity of the box, well, we can use our kinetic energy formula. Ek is equal to a half mv squared. Let's get v by itself. 2 Ek over m is equal to v squared. Therefore the square root of 2 Ek over m equals v, which is equal to the square root of 2 times 1 over 0.2, which is equal to the square root of 1 divided by 0.2, no, 2 divided by 0.2, which is around 3.16 meters per second. So that is the speed that a block of mass 0.2 kilograms, if compressed against spring Z, 10 centimeters, would launch off at, if it was launched. The next question we want to do is figure out if we compressed that spring a further 10 centimeters. So I'll shrink this down. So compress Z a further 10 centimeters. What is the change in Ek and V? So the change in Ek, we should first figure out how much spring potential we have in the 20 centimeter compressed Z spring, since it was 10 centimeters to start off with, and we're compressing it a further 10 centimeters. Now the spring potential is a half kx squared. That's a half times 100. You know what I've done? Sorry, I'll just go back and correct a mistake I had. Back here. Back. Back when I did part A, I've accidentally assumed K is equal to 200 here. Change that value to 100. The kinetic energy changes to 0.5 joules. This changes to 1, and I get the square root of 5, which isn't 3.16, it's 2.23. 2.23. There we go, hope that's corrected the mistake. So the new spring potential is a half kx squared, which is a half times 100 times x, in this case that's 0.2 squared, 0.5 times 100 times 0.2 squared, that's 2 joules. So the change, which is also equal to the kinetic energy of the box. So the change in kinetic energy of the box is equal to 2 take away 0.5 or 1.5 joules. Just by compressing it a further 10 centimeters, we increased the amount of kinetic energy in the box at the very end by a factor of 4. Now let's figure out the change in velocity. So the final velocity of a box, mass 0.2 kilograms, that was compressed 0.2 meters, is equal to, we use our kinetic energy formula, EK is a half mv squared, 2ek on m square rooted equals v, which is equal to 2 times 2 on 0.2, which comes to 4.47 meters per second. So the change in velocity, the velocity of the box under compression 0.2 meters was 4.47. The velocity of the box after being compressed 0.1 meters was 2.23. So delta V is 4.47 take away 2.23, which is, depending on which approximation you use, I have 2.24. You may have something very close to that. This is a nice result because it shows you if I compress a block 0.1 meters against a spring and then release it, I get a final velocity of 2.23 meters. If I compress that same block another 0.1 meters, I can double the velocity. I can add another 2.23 meters. If I compress that block another 0.1 meters, it'll go up again by 2.23 meters. So the final velocity of the block goes up linearly, just like the Hooke's constant graph. That's something to think about. It comes from the relationship between x squared here and v squared here. The next video we'll do incorporates the forces of gravity into these spring questions.